Okay, welcome you all to this week's Samvaad talk. Today we have Professor Meenakshi speaking to us about some of our research work. So just to introduce the speaker, Meenakshi is an Associate Professor and Warden, Women's Hostel at IIIT-Bangalore. Prior to joining IIIT-Bangalore, she worked in R&D Division of Honeywell Technology Solutions Private Limited for 7 years and was visiting scientist at IIIT-Bangalore. Meenakshi did her PhD in Theoretical Computer Science from Institute of Mathematical Sciences, Chennai. Her research interests are in formal methods and architectures for embedded software and software testing. Meenakshi is a part of Software Engineering Lab at IIIT-Bangalore. She teaches courses on design and analysis of algorithms, discrete mathematics, theory of computation, software testing and automated formal verification at IIIT-Bangalore. Also, just to mention, Meenakshi has recently been elected in India's Chapter Council of PCM, so which is a prestigious. Welcome, Dr. Meenakshi.
Yeah, thank you. Thanks for the nice introduction, Sujit. So I'll tell you a bit about my work. Today I essentially work on formal methods. I am not an engineer. I have a degree in maths and theoretical computer science. So it's essentially some kind of theoretical computer science, but to make it slightly more trendy, we give all these names to it. But it's just basically theory with some applications to it. So in this talk, I have prepared to talk about. So our lab essentially survives with a large number of part-time students who come with their own research agenda. So the one condition that I always take them in is that you must be interested in embedded software, you must be interested in testing or verification. If you're not interested, we can't work together. So we do, as long as this broad scope is there, we do a lot of work. So I have prepared to talk to you about 3 of the pieces of work that we've done along with the research students. Based on time, I could restrict it to 2 or discuss about all 3. So I'll begin with an introduction of what I mean by embedded software. So these are examples of what embedded software looks like. So the first one, the one that you see on top where it says robotics is a robot, not a humanoid robot that is making waves in newspapers. This is just an industrial robot. It has 1 or 2 arms and it can do routine tasks like picking, placing objects, welding, painting, things like that. There is a lot of software that runs in a robot like this, some amount of machine intelligence also. So we are interested in the software that runs in these kinds of robots. Of course, we all know aircrafts and unmanned aerial vehicles. Almost everything in an aeroplane, every core control functionality is done by software. It could be autopilot to landing, to takeoff, to fuel control, to power distribution, to cabin entertainment, to cockpit displays. Everything is done by software. Similar to avionics, we also have automotive. A typical Maruti Swift car will have a few million lines of code running in it, right? So automotive, transportation, railways, it's a sample of that. And we all have to stay catching up with the trend. So the trend for our kind of work is IoT. So IoT, I'm not interested in the physical things aspect of it. We are again interested in the software that runs in an IoT system. And things like these are generic languages which will come in any kind of embedded control design. Like, for example, it could be the design of an autopilot, it could be the design of a cruise control system, or even our lifts that take us up and down the various floors. So this is what I mean by embedded control software. So what is not embedded control software? Software that runs Citibank online is not the kind of software that I'm interested in. Our methodologies, techniques that we are presenting today will not work for that kind of software. A software that displays stock rates, as the thing goes by, right? So that is not embedded control software. So those are large enterprise software, web applications. Those are different kinds of software. Our techniques will not work for them. Our techniques are exclusively, the thing that I'm talking about today will exclusively work only for these kinds of software. So how do I characterize such software? They don't run on the internet, they don't run on the web. They typically run on a real-time platform a real-time platform that is almost always proprietary to somebody. It may not even be open source. A company owns it. Company makes it, owns it, and looks after it for a few decades. That's how embedded software are designed. The software is tightly coupled with its environment. If I have an operating system that is sold by a company called VxWorks, it will run in whatever VxWorks is compatible with. It may not run in anything else, right? So it is very tightly coupled with the environment that it runs. It's typically distributed. What do I mean by distributed is that several processes, tasks run simultaneously. It is real time in the sense of hard real time. So there are things like interrupts, timer sets, resets, things like that happen. And such software is also very safety critical. What do we mean by safety critical is failure of that software is not acceptable. So suppose you're working with your mobile phone or with a Windows operating system, routine thing that we do if something doesn't work is to restart. Things will always work. Shut it down, restart, next time you will be able to do it fine. You can't do that to an autopilot as it's flying an aircraft. You can't shut it down, restart, and hope that it'll start flying it now properly, right? So a failure could mean loss of life, heavy loss of life and finance. So they are safety critical. Because they are safety critical, there is a big deal done about. So I can't say that tomorrow I have a very niche autopilot software that I have developed. You can't go and sell it to a company like Airbus or Boeing. Your autopilot software has to be certified by appropriate authorities. And certification is not an easy job. It is done by, like in India, for a civil aircraft, an aircraft that flies passengers, DGCA is the certifying authority. In the US, it is FAA. So these people certify a software. So this is only for aircraft. So similarly, for every kind of embedded software, there are certification requirements. There are regulatory requirements that tightly control what the software should be like, how it should be tested, and so on. So as I told you, we can't, but suppose it's malfunctioning, we can't say, okay, no matter, doesn't matter, shut it down and restart, everything will be fine. That doesn't apply for embedded software. So it's been known for many decades that this is a very generic statement, that it's very important to develop that methods that increase our confidence in the correctness of safety critical systems. Maybe I'll come back to this, or maybe I can go through it. Typically, the kind of software that we work with, these days the buzzwords in software development are Agile, Scrum, XP, and stuff like that. Those are just process level things. But how is the software that we work with developed? It's almost always developed using this V model. Requirements are written first, and then somebody does an architecture and design. This includes system and software aspects, that's refined. Somebody does coding and testing. And then this is given a lot of importance for embedded software. So much so that if you remember the classical models, usually people stop here and then they would say release or maintenance or something like that. But when we work with embedded software, we usually give a lot of importance to this side of the V model, because testing is given huge amount of prominence to embedded software. So we do several levels of testing. As a person is writing code, he or she does unit testing. Then we put together the software and hardware components and do integration testing. Then we do system testing. System testing, you would have seen popular examples. If you go to Aero India show, I don't know if you've been to, Bangalore hosts this every year, you can get to see a system. You can get to see how an Airbus cockpit will look like, how a Boeing cockpit will look like. You can simulate and test. And if you're in the automotive sector, people actually put the software in the car and crash test it to see. We can't do that for a plane because it's expensive, but people test like that for the car. And finally, after release, they do what is called acceptance testing. So typically, a lot of effort in embedded software goes on all of these phases and a good number of effort on testing. General ballpark figure about empirical studies in software engineering has shown that for a normal software, assuming that you don't classify it, about 55% of the software development effort is spent on testing. So for embedded software, it is probably more than 55%. So other thing to note while designing embedded software or even in other software, this is again empirical studies, is that so suppose you go through these phases in the software, right? Suppose I write what I want to write code for, then I architect and design, then I do my low-level design. Suppose you find an error in one of these phases right there before you start coding. right? You say there is something wrong, two requirements are inconsistent, right? I have done my design wrongly, one requirement contradicts the other. You realize that before you code. So it's not too difficult to imagine that once you realize this before you code, you can fix it then and there and get going. The cost of the defect won't be too expensive in terms of cost and the time that it takes to fix it. Suppose you fix it here. There is a defect that's inserted somewhere here and you do code for it, and while testing you fix it. Then also it's all right. But if you fix it here or here, then it's a little more expensive than when it was found here or here. Because here you have a large piece of software, typically a few million lines of code. So in testing, there is this classical problem of if you find a defect, how to isolate it? How do I know where the defect is? During integration testing, fault isolation becomes a big problem. So you spend a lot of time, and then suppose you are able to isolate, you have to figure out, let's say it was a buggy design. So you have to go back, fix the design, write code again, test it again, and integration test it again. So the cost is higher. The cost goes higher if you find it here. After you release, the cost is unacceptable, because if it's safety critical, it could mean loss of life also. So that's what this plot says. This plot says that as I go up, the cost to find and fix an error increases drastically. So our talk is about embedded software and verification techniques on embedded software. That's what my talk is about. So I'll quickly summarize what are the popular verification techniques. Verification, I use it in a generic term. It includes everything. It includes testing, a lot of things. So the simplest verification techniques that is practiced by almost all large companies is what is called peer reviews or code reviews. These are reviews, so a team member or a software quality auditor, SQA as they would call that person, would sit and read through your code. I mean, this might sound like a funny thing to do, but they do it, right? So, and the code is a few million lines long. Obviously, you cannot read through the whole code manually. So you have tools that annotate the code, that present the code in bits and pieces, that help you to read through the code in a slightly assisted way. But this is a very popular verification technique. That's why I put the manual within brackets. Somebody still goes through it manually, but sometimes part of it can be tool assisted. And empirically, it is shown that there is a study by Carnegie Mellon University which shows that about 53% of coding errors can be found by just letting somebody else read through your code. So that's a non-trivial amount of coding errors that can be found. And it's a fairly standard practice that people do. In fact, if you're an SQA in an organization like FAA and all, it's a very well-paid job. It's a great career path that students can take. Unlike a developer where the growth is slow, here the growth will be quite fast. So the next popular verification technique that we all know is testing, right? It's like a common man's word. Testing begins right from the time we begin to write programs. You could have written program as a 9th standard or 10th standard or 11th standard student. You have to convince your teacher that your program is correct within quotes. So let's say you write a program to convert centigrade to Fahrenheit or something like that. You give it a few values, run the program, and then observe the output and see this program produces what I expected it to produce, so my program is correct. We do this whenever we write programs. All of us do it. It could be a classroom project, it could be a larger semester-long project, or it could be professional code that you write. For whatever it is, you do testing. So what happens in testing? I have a piece of code. I provide it a sequence of inputs. These are called test cases. The code runs, assuming that it doesn't create any compiling issues and it runs reasonably smoothly, which is a big deal because many of the students' code will not even run. But assuming that it runs smoothly, it will produce an output. And then you look at the output. So that output that it produces is an expected output. So you have an idea of what it should produce as output for it to work correct. So you observe the output. Suppose it produces the same output, everybody is happy. You have tested the program, you go back. Suppose it produces a different output, you say, yes, I found an error because this is different from what I expected it. So the program has an error, right? So error is detected if there is a mismatch. Clearly, testing is the most popular verification technique. There is a popular statement by Bill Gates who says 55% of Microsoft's engineers spend their full time doing nothing but testing. 55% of Microsoft's engineers spend their time doing entirely testing. So it can't be replaced, it will exist forever. Without that, software will not exist. Right? So what are the advantages? What are the disadvantages of testing? Advantage is that it's the single relatively well-practiced technique. It's heavily automated. There are all kinds of testing tools that are available, commercial, open source, that will do a lot of the testing automatically for you. And it is applicable, it checks many aspects of software at the level of a single method or a function to large pieces of software integrated, several million lines of code. It's applicable to all kinds of software. It could be a web app, it could be an enterprise application, it could be a complicated animation that runs, right? It could be whatever it is, augmented reality, whatever it is, testing will always do the job. The disadvantages are exhaustive testing is not possible. So even if you take a small program, like I told you, right, that converts temperature given in Celsius to Fahrenheit. So you have a formula, you apply 5 by 9 into F minus 32 or something, and then you write the program. And then you want to convince yourself and your stakeholder that the program is correct. What do you typically do? You give some values, you say 0, some 1 or 2, 3 values, and then you run it, and assuming that you've written the code correctly, it will produce correct output. So what does that tell you? Strictly speaking, mathematically, all that you have done is that for that n number of test cases that you have written, you have convinced yourself and your stakeholder that the program is running. It is wrong to say that the program that I wrote to convert something from Celsius to Fahrenheit is correct because I have tested it on 5 inputs. Somebody can come and say, no, don't worry, you test it on 1,000 inputs. It is still wrong to say that my program will be correct, right? Because if you take these to be real-time or floating point values, based on the processor that you have, unless you exhaustively test it, you cannot say that my program is correct. And exhaustive testing is not possible. It's not possible mainly because it's not practical. It may not be needed, right? And even if you have a super fast computer, exhaustive testing, time-wise, takes a lot of time. And the second point is Dijkstra's famous quote. I don't know if you know about this, a computer scientist called Edgar Dijkstra. He was an early Turing awardee for one of his, there is no Nobel Prize in computer science. His highest award in computer science is the Turing Award. So Dijkstra's quote, that is. So he says testing can detect the presence of bugs. It's very good. If your software has an error, testing can find it. It's very good at finding it. But using testing, you cannot give a proof that there are no errors in my software. By a proof, we're looking for a mathematical proof. A pair. Could be done by a tool, could be done by pen and paper, but testing cannot do this. Testing cannot prove that my software is free of errors. It cannot do that. And typically, testing is not considered adequate for safety critical systems because they are highly distributed or concurrent, and testing is not, it's not testing techniques' strength to detect these concurrent bugs. They come very deep in the design, and they may not get revealed even in complex input sequences. So apart from, so we have peer reviews, testing. So there is a third technique called formal verification, which is what my talk will be about. So basically the word formal means that there is some amount of formalism involved. Formalism means some amount of discrete maths for us. So it's a class of techniques that developers and designers can use to construct systems that operate reliably. So it's considered complementary to testing and simulation. So you can't say that I've formally verified my software. We'll understand what it is. So you do away with testing. That is typically not done. Testing you always have to do. In addition to that, you could formally verify to increase confidence in the system that you're developing. So what is formal verification? So formal verification is based on what we call formal methods. These are terms that you would have heard. Basically, formal methods are a whole bunch of mathematically based notations, techniques, and tools that do two things. they specify a system, they verify a system. So we'll understand what specification means. So suppose I tell you, you write a piece of software to do something, right? If you're in Professor Dinesha's OAD course, he will say, your first thing that you have to do is to list the features that you want to develop over the semester-long project that you want to develop for whatever, the miniature version of Facebook or something like that. These are the kinds of things that he gives. So how do you write your requirements? You typically might write it using Word or whatever your editor is. Ultimately, you will end up with an English document written using the language of English that describes what your software should be written for, right? So that document is a specification document. So you use that as a basis to design and develop your software and test your software to see whether it meets its functionality or not. So when we formally verify, we are not happy with the English written specification document. We usually ask for specification written in a language that has some more math in it. So typically we write requirements about a system in a mathematical language. So that math language could be, so typical mathematical languages that we use are logics, set theory, and maybe sometimes some kinds of graphs. UML, Unified Modeling Language, also has diagrams for writing specifications. The diagrams that are used for writing specifications in UML are use cases, activity diagrams, finite state machines. They all have semantics. They are some kinds of graphs, so they are acceptable as documents to write specification in. And then we model a system. Typically you write C code or Java code, then you come up with design maybe as some set of class diagrams, some state charts, some state machines, right? If the rest of it is code, but we are not happy with code because code sometimes can be misinterpreted by others. So we want to understand what the code means. So we try to model the code also in an appropriate mathematical language. So we first write down what we want the software or the system to do in a mathematical language. Then we write down the system itself, which could be the software or system, in another mathematical language. I'll tell you what those mathematical languages are. Once we have these two, then you could verify. By verifying, we sort of prove formally that the system meets the requirement. So what kinds of proofs could be done? So somebody could take pen and paper and do a proof by hand. Just a normal good old proof. You could work out. Suppose you have a piece of software that uses, let's say, merge sort for some reason as the first step, right? So you could prove that the first step is correct by doing a proof of correctness of merge sort, right? So you could, and then you could keep doing these proofs of correctness. So that's called by hand verification. So early propaganda for by hand verification was done by people like Sir Tony Hoare, Edgar Dijkstra, and a few others, all of whom got Turing Award for their proposed techniques of writing a pen and paper proof, right? Sir Tony Hoare is still alive, working as an honorary researcher in Microsoft Research. They say Microsoft opened an office in Cambridge because they wanted Sir Tony Hoare to work for them, right? So he was one of the early Turing awardees for designing by hand verification techniques. Just do a pen and paper proof. There are techniques that you could follow: proof by contradiction, proof by induction, whatever you could do, right? The second thing is semi-automated proof. Parts of it an algorithm will do for you. Some lemmas that are obvious, some propositions that are obvious, an algorithm will do it for you. You just do the main part as a human, right? So that is semi-automated because it's partly automated. The third kind is you can rely on an algorithm itself to do the proof, right? So these three kinds of proofs you do. Typically, there are three popular techniques based on what kinds of proofs you do for what results. One is called model checking. One is called theorem proving. One is called program analysis. These terms are quite generic, but that's how they are named. So theorem proving is done even in maths, but when we say theorem proving here, we mean something specific. Maybe I'll skip that slide. So what I'll do is, in my talk today, I'll take embedded software, going back to embedded software, and talk about one work where we have used theorem proving to verify embedded software. So I'll tell you what theorem proving is. And one piece of work where we have used program analysis to verify another kind of embedded software. So I'll tell you what that piece is. And for another kind of embedded software, we have developed a new bag of algorithms for testing. So that's what my talk will be about. 3 kinds of embedded software. One bunch of work that we have done in trying to develop test case algorithms, which is classical testing at the system level. One bunch of techniques where we have used theorem proving to verify, and another bunch of techniques where we have used program analysis to verify. I won't talk about the work that we have done on model checking. So I'll introduce you briefly to what program analysis is. So as the term says, you have a program. So you have a program written in C, Java, Python, whatever it is. You're trying to analyze the program. So we choose the term analysis because we believe that these are techniques that are different from testing that program. It's not testing the program, it's analyzing the program. So once we have a piece of C code or Java code, we don't take the code as it is. We work with some kind of an abstraction of the code. Unfortunately, I won't be able to concretely introduce to you what an abstraction is. But one simple way of looking at it is you all must be familiar with things like a flow chart or a control flow graph of a program, right? So typically, what does it concentrate on? Initially, you do a whole set of initializations, let's say, and then at some point, if there is a branching or an if statement, the flow chart will depict the branching, right? If there is a loop, the control flow diagram or the flow chart will depict the loop. But it may not depict the full details of exactly what happens in each of the statements that run one after the other. So typically, we abstract and represent a program as some kind of a graph. So the various kinds of graphs that we deal with when we work with program analysis are graphs that will discuss how control flows in a program. Like for example, if you have just a sequence of assignment statements, control flows sequentially in a program. If you get an if statement, then the program control flow branches into true and false. So control flow graph talks about these kinds of things. Along with control flow, we could talk about how data also flows. Data in a program is a set of variables that are involved in a program. Let's say you have a variable, let's say if you have an if statement which says if x is less than 5 and let's say flag is true, then you do something, else you do something, right? So let's say the value of x was 3. So the flag was true. So the if statement turns out to be true. So you take the then branch. Then in this case, x is reset to 5. If you take the else branch, instead of x being reset to 5, it gets reset to 7, right? So data, the way data flows, the value of data varies. We track that. So we call these graphs as data flow graphs. This is usually finite. This could be a large infinite graph because typically a program will have several different variables. Then the other thing that programs do is they have one procedure calling another procedure, one function calling another function. So the third kind of graphs that we deal with when we do program analysis are call graphs that represent procedure calls or function calls. We also work with this structure lattice. So lattices are partial orders of certain kinds. So partial orders are graphs of certain kinds. I don't want to go into those details, but lattices are graphs that can represent abstractions of programs. So what does program analysis do? It takes a piece of code, works with one or more of these kinds of graphs. Maybe 2 of them could be clubbed together and stuff like that. And then it basically detects a lot of low-level programming errors. So what do we mean by low-level programming errors? I'll show you an example of what a low-level programming error is. Like for example, one low-level error is if you have a variable that is used but not declared, then a compiler will find it. You're able to understand? Routine compiling will find it. But the other way, suppose you have a variable that's declared in a large piece of code but never really used, right? It may not be a big deal if you have a large server and an enterprise software, But in embedded software, it is a big deal because you don't have too much memory and there are constraints. Everything has to fit into that particular processor in the car, right? So if there is a variable that's declared and not used, it better be detected. So similarly, dead code, presence of dead code in the sense code that can never be reached. Somebody wrote it, it just stays in that corner, no use. Then there is a risk of a division by zero occurring. Testing also detects division by zero. Things like these are low-level errors. Some of them are difficult to find using testing. So program analysis can do it. Typically, two bags of program analysis are there. Static means it does it without executing the program, without running the program. This means it does the analysis by running the program, dynamic. Usually, tools are available. But the general problem of program analysis, suppose I give you a program and I ask you find all the declared but unused variables in the program. This problem in theoretical computer science is an undecidable problem. By an undecidable problem, what we mean is that in general there is no algorithm that will solve it for all classes of programs for all variables. So there are no algorithms to do it. So what tools do is they work with heuristics. Sometimes the results they give might be false positives. Because the problem that they were, even to check whether a program will halt or not is undecidable. You can't do it automatically, right? So we live with that limitation. So program analysis does that. So I'll go ahead and tell you the program analysis works that we have done. So we have this sponsored project from ABB. ABB is a company that has 3 or 4 major divisions. One of the divisions is their robotic division. So they make these industrial robots. The robots look like this. So you can see in that picture, 2 robots are working. There is some kind of assembly line. Maybe they are welding or something like that. So we call these things as robots. They can be thought of as essentially one arm, like our arm. So they call it robot manipulators. So it has several axes, like you see axis 1, axis 2, axis 3, axis 4, axis 5, 6 axis, 7 axis based on what can turn, twist and thing. It always holds a tool at the end. And with that tool, it can paint, weld, do whatever it wants, right? So this is what is a robot. So these are multi-axis industrial robots that work in industry setting. They are not humanoid robots or things like that. Mobile robots, swarm robots, they're not like that. They're just pure industry robots. So typically what they do, they can weld, paint, pick, place, do all these things. ABB manufactures these robots and it also lets the user program these robots. So the language that ABB has to program these robots is called Rapid. It's an ABB proprietary programming language. But let's say Yokogawa will have some other programming language to program their robots. They're all proprietary. Typically, that's how their businesses work. But they all have similar features. If it's industrial robots, then the programming language will have very similar features. So if you do one work for one class, then one specific language, then you're spanning. Your algorithms that you've developed will usually work for other programming languages also. So typically, a robotics engineer can program these robots using what is called a teach pendant. That's like a handheld device that they use. In fact, in our institute in Professor Prasanna's lab, there is an ABB robot with the controller and a teach pendant available. So you can program it. So their intuitive interfaces are given where you tell the robot what to do, or you can write directly rapid code, right? So I'll tell you how rapid code looks like. So this is how instructions in rapid look like. So if you read the first one, it says wait time. Wait time can be thought of as a command or a keyword in rapid. It says 200. So it means it tells robot wait for 200 seconds before you do the next statement that comes in the rapid program. This one says that there is an interrupt variable called INTR. It disables that interrupt. This is a rapid command for that. So read this as move L. So the robot has an arm, it's holding a tool. The tool that it's holding is called tool 1. Some tool, it could be a paintbrush, could be anything. So it's holding a tool called tool 1. It says move this tool linearly. Linearly means along a straight line. That's what move L says. From the point P1 with velocity 500, the speed at which you want to move your arm, to within this zone. So the zone, usually if you see here, this whole work area is divided into grids. Okay? I don't know if you can see the grids clearly. And then there is an X, Y, Z fixed for that. Right? So Rapid has instructions like these. You can say you wait, you can set or reset interrupts, then you can do move linearly a particular, from beginning from a point with a certain velocity into a zone, whatever you're holding in your hand. Right? So you just have to write this much in Rapid, and the rest of it we don't worry. This instruction and the controller will calculate torque that is needed to apply to move linearly and all. We don't worry. Right? So it has instructions like these. Then it has standard data types, the usual ones. Numbers means integers in Rapid, string, boolean, array, and all. And then it has these complex data types. So if you read this says what is that particular point in X, Y, Z coordinates. So normal three-dimensional coordinate system. So if you remember this one, we saw an instruction which says move linearly starting from point P1 into zone 10. Right? How do I specify a point P1? I specify it like this. So this specifies point P15. I'm not going to go into the details, but the first three, this part specifies the thing in three-dimensional system. Then this one specifies what the tool looks like. So just to give you an idea of what happens, I'll just go back to this picture. So a typical scenario looks like this. This can be thought of as a room in which two robots are working, right? So the room has an XYZ coordinate system. If you see this robot is facing this side, this robot is facing this side, right? So the XYZ for the room, if you think of it as a normal coordinate system, the robot hand might be like this. So its XYZ has to be moderated with reference to the XYZ of the room. We're able to understand, right? Another robot, for example, a robot could be suspended from the ceiling trying to hold something, and another robot could go and paint it, right? So that XYZ of that robot has to be moderated with the XYZ of the room, right? And then you have to be able to define what one point means. So you can write these kinds of specifications in Rapid, this kind of declaration in Rapid which tell you what one point is, right? So apart from this, Rapid has a normal thing that you would find in a C-like programming language. It will have if then else, it will have for, while loops, it can have procedure calls, it can have interrupts and exceptions and things like that. It doesn't have pointers, malloc, and it is not at all like Java, no classes, objects, nothing like that. It's just a classical good old C-like language, but without pointers, without files, dynamic memory allocation, but with a lot of complex data types like this, right? A lot of complex data types which tell you how to do it, right? So here is, I don't know if you can read this. I was trying to squeeze in the whole code into, so this is one Rapid program. So the way to read it is that, so this gives you all the declarations. So for example, 4 points are defined, R1, R2, R3, R4. Then there is a main procedure, a lot like in C, which right in the first line calls another program called simple bug. This is the function simple bug. And then it does some initialization. Then it calls another procedure called set to 0. And then this is like, if there is an interrupt, then you call this error message, which will trap. It's like a try-catch kind of thing that you can think of, but written for Rapid. And then it will do something. And then finally, it will call this draw shape, which will draw maybe a square or a rectangle here. So this is how a Rapid program looks like. So just to summarize, it has a main procedure, several complex data types, several procedure calls. There could be interrupts that alter the procedure call. Like for example, one typical thing that we classically use is that a robot gets this stack of papers, and it can either draw a triangle or a rectangle or a square in that paper. So as it draws, one robot draws, another robot arm pulls out, keeps the paper aside. Then the next paper comes, the next robot draws, pulls out, keeps the paper aside. So papers get depleted. So when the paper count reaches less than 10 or less, there is an interrupt set to say somebody please come and replace more paper, right? So based on that, this control flow that will finally draw a shape can get altered if it runs out of paper, right? So these kinds of things typically happen in Rapid. The important thing is that these interrupts can come from anywhere. They could be system-driven interrupts, sensor-driven interrupts, because there is a sensor that tells you how many papers are there and all, and they can alter the program control flow. So the project that we did, the work that we did with ABB was to develop a program analysis framework for rapid-like programs. So the difference is that there are lots of program analysis tools available for a programming language like C. Yeah.
So are these programs written for separately for individual robots, or is it a single one program for all the arms?
So the programs can be grouped in several different ways. So usually robots, some kinds of robots belong to a family, which is family's lead is the controller. So the head of the family is the controller. So IRC5 is one ABB controller. IRC5 can work with any 3-axis robot. So any 3-axis robot will, so you can write rapid program for IRC5 series. It can be run, programs run on the controller, not inside the robot arm. Robot arm may not have execution capabilities. So the controller will run the program by talking to it. So typical program analysis techniques like those that work for C will not work here, because the data types are horrendously complex. There is a lot of numerical methods that goes into understanding what this means for the robot arm, which is the position that it's trying to define, for whom, right? So we've developed a program analysis framework. This in nutshell is that framework. So a lot of it is what we do for any program analysis framework. There is no deep fundamental research or anything like that. Like for example, things like extraction, parsing, CFG generation, all this parsing and all can be done very fast for any programming language. It is not very difficult to figure out how to parse. CFG can also be generated, but here there are procedure calls, as I told you, all kinds of procedure calls. Procedure calls work slightly, it's not like call by value, call by, it's not like that. It works based heavily on interrupts and other things. So the work that is difficult to do is to generate interprocedural CFG. Once you have the interprocedural CFG, we've developed an analysis engine which has pattern matching, data flow kinds of algorithms, a set of rules and all that, and ultimately it will do program analysis, right? So the kind of errors that you can detect are these kinds of errors. So you can detect array out of bounds array access, standard error. You can detect the presence of an infinite loop, right? While something is always true, it is very easy to write such programs and make mistakes in rapid. You can detect division by 0. You can detect unused variables, dead code. You can also detect things like robot boundary violation. So if you go back to this figure, they will have a requirement which says that, so what will happen if this robot moves too fast or the two arms should not collide, right? Because this might be a room where a human doesn't go normally, or it could be dangerous. So robot has something called a boundary that's specified as a part of a requirement, and it's an important property in rapid to prove that the robot will stay within its boundary. These robots don't move in the sense that the base of the robot is drilled and fixed here. Only their arms move. The robot by itself doesn't move. So its arms should not cross the boundary. So those kinds of things can be automatically detected with our program analysis framework. Yeah. 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 So I said no. So there is always false positive in a program analysis framework. Every program analysis tool can always have false positives. So I can say that, yeah, I will say that there is an infinite loop. Whether there is an infinite loop or not, it may not be there. This is not only true for rapid. Even the best known program analysis tool for C can have false positives, because we can't even check whether it's the same problem, the halting problem, right? We are working with undecidable problems. So yeah, so when I say we can automatically check these, what I mean is that there could be false positives always. So any program analysis will have false positives. So what usually people do is that they test it on benchmark examples, and then they say that, see, my program analysis framework has very less false positive rate. That's how.
There are false positives, but there are no misdetections.
No, that is not.
That's not allowed.
So yeah. So it should be sound. Your program analysis framework should be sound.
It's okay. Obviously, there is a constraint that probably.
No, we don't worry too much about. I mean, you understand what he's saying, right? We usually worry about false positives, and there is a reason to worry about only false positives, right?
No, but generally,
if there is no.
Where we say that we want to reduce the false positives, there is always a chance that you might miss something.
No, here also, see, because yeah.
You want to say that I don't want to have any misdetection. With that constraint, I'll minimize my.
Yeah. So usually what they do is so there are these benchmarks available, and so for popular languages like C or Java, there are standard benchmarks available. Suppose you have a new program analysis framework, you could benchmark it against that and say you did better than all these guys who were there before. So it's very important for commercial companies like Coverity and all who develop these tools actually. So, but because here we are working with one proprietary language, so we go by if the engineers are happy with it, that's good enough for us. But the problem is undecidable. So if it says something is found, it may or may not be true. We live with that. There is nothing we can do about it. So we published our initial work in last year's IIIT, and the full this analysis engine sort of got completed, and we applied it to a few other proprietary languages of ABB, and that will come in ETFA in September this year. So this is one piece of work that we did on program analysis. This was done along with my PhD student Avijit. He took about a year to get this framework implemented. Yeah. Yeah. In fact, many, not only MATLAB, even if you have Visual Studio or I don't know, IBM's Rational Rows, any development framework that you work with will always have inbuilt program analysis features made available. So MATLAB has a very good one, but Rapid works inside an ABB proprietary framework called Robotic Studio. In which getting these things out is not easy. You know it's proprietary, so it may not give you the interprocedural CFG and things like that. So what is applicable for C or MATLAB may not have been applicable for Rapid. So that's what I said. So till here, the bag of techniques that we used is all the same, no big deal. What will work for MATLAB will work for C, will work for this. But these parts are difficult. Like for example, to develop a pattern matching engine that will include these special data types is not typically done in C, or MATLAB might do it for its data types, but we did it for Rapid because you know, the nice thing is once you write an instruction like this, Rapid has the internal kinematics which will ensure that it will move linearly. So we take it to that level of abstraction and leave it at that. For us, it's just a complex data type and an instruction. So this is one piece of work that we've done with Rapid, and it is something that we were able to convince at least ISRI and ETFA are good conferences, and it's not easy to convince those PCs that there is good work. So I'm happy that we did that. So next I'll talk to you about one work that I did with an MS student who recently graduated on theorem proving. So this is the second formal verification technique that is very popular. So the word says theorem proving, so you prove some theorems, it's literally that. But partly you use a human being to prove the theorem, sometimes you use a tool to prove your theorem. So typically, if I prove a theorem, then I need a language to write my theorems in. The language that we use are logic and set theory. I don't want to get into, most of you would have heard about propositional logic. First order logic works with variables that are not of Boolean types. Higher order logic, you can quantify over relations, functions, and things like that. Set theory extends logic to work with all kinds of sets. And what you want to verify, your specification is given as a formula in logic. Your system is also given in logic. And then you do a proof that derives the specification from the system designer algorithm. So this derivation means that there is an underlying axiom system. I again won't get into the details. So derivation means that you can do a step-by-step procedure, a proof, step-by-step proof, which we call a derivation. Each step in a proof is called a derivation in the language of theorem proving, and then we can do a proof. So again, this cannot be fully automated because even for first order logic is a very elementary logic. For first order logic, elementary properties like satisfiability and all are undecidable. Undecidable in the sense that I can't do a proof automatically. First order logic is undecidable. So higher order logics will obviously be undecidable. So typically proofs are done partly by hand or semi-automatic. So theorem provers are tools that assist you in theorem proving. They can do a proof by hand or automatic. So I'll talk to you about one work that we've done in theorem proving. So the area embedded software that we applied theorem proving to is in IoT. So I don't have to introduce you to IoT. We all know what Internet of Things is. It connects computing devices, sensors, actuators, people, whatever, right? It's getting prevalent in several industries. What I want to focus on is the IoT protocols. So again, IoT protocol means I'm not talking at the physical layer or data link layer and stuff like that. I'm not talking at the level of TCP/IP or UDP and all. I'm talking at the level of application layer because we are only interested in software. So typical application layer protocols in IoT are, I don't want to, so this is message queuing telemetry protocol, MQTT. This is an application layer protocol. MQTT-SN is another application layer protocol. CoAP, XMPP, AMQP, these are all application layer protocols. They work on top of TCP/IP or UDP. So if you know the layers in the stack, I'm talking about above MAC, purely at the application level. So in IoT, these are specific protocols. These XMPP and XMPP is still under ballot. I think these two are still under ballot, but these have been used and they are available as a part of IoT architectures that companies like Cisco and Microsoft and all give you to develop your application software. Typically for IoT, what is important property of a protocol? It should work with low power because the devices can run out of batteries very fast. It should work with low bandwidth because the span of it could be very far. Again, everything is low footprint, right? Low memory. It should support very small authentication protocols and security. It should have inbuilt self-recovery mechanism. If it dies out of battery, then the protocol should be able to back up data such that when somebody comes and replaces the battery in the end device, it can restore the data. It should be able to do resource discovery, commit to certain quality of service, and so on. So what we did was to model some of these IoT protocols in one theorem prover and verify its properties. So you might ask, why did you bother doing this? So one reason is when MQTT, this protocol, so MQTT is so small, so we all know that SMS that we use, many of us don't use, that's almost free of cost. It uses a very elementary protocol. MQTT is even cheaper than SMS. So when MQTT was being under ballot, there was an error found. So it was committing to a certain quality of service level. So if it commits to, let's say, a QoS 1 or 2, it means that even on the other side, if the client is dead, it will keep the message that it's meant for the client, sense that the client becomes awake again, and resend it. Unlike QoS, there is something called QoS -1, quality of service -1, which they say is fire and forget. You send a message, you forget. You don't bother about whether the receivers received it. You don't care about acknowledgement and all. Whereas if you commit to QoS 1 or 2, then it is your job to ensure that the person receives it. The other end node could be dead. There could be no battery. But when it comes alive, it is still your job to ensure that the message is received. So MQTT committed to certain QoS levels, and it was found using normal testing, software testing, that it didn't meet that. So then there was this big debate, and in this thing, the committee recommended that formal verification could be a good way to resolve these kinds of issues. So we verified it using a particular theorem prover. So the way we did it was, so my student first did a study. So she took 4 protocols, MQTT, MQTT-SN, CoAP, and XMPP. So these were identified to be the features that need to be tested. Classically, they are tested. for every protocol that is under ballot before being released. So, for example, what does the protocol support? Does it support asynchronous message exchange? Does it support REST architecture and things like that? And this is just a mention, we don't really worry. Does it work on TCP/IP? Does it work on UDP? Because based on that, the security that it provides is different. Will it support unicast, multicast communication? Then this is what I was talking about. What QoS stands for quality of service. So quality of service, MQTT, for example, says at most once, at least once, exactly once. So it means that message will be delivered at most once, either delivered or not delivered. That's what it means. Here it means that message will be delivered at least once. Here it means that duplicates will be removed, even if there is a loss on the other side, and the server will ensure that the message is delivered exactly once. Right? So you've not received an acknowledgement because the client is dead, no battery. So you resend, but you have to be careful. Ultimately, the client should get the message only once. So using MQTT will guarantee this, but there was a bug in this. So that's what motivated the need for us. So persistence means ability to retain data. Proxying, caching are all related to persistence, and a few other things. So we did this study and we found out what supports what. Like for example, all of them support persistent session. MQTT supports only unicast. Unicast is point to point, whereas the rest support multicast also. So this helped us to compare the features of protocol, and then we did this elaborate modeling exercise in a particular theorem prover called event B. I'll briefly introduce you to event B. So it uses set theory and first order logic for modeling. It has very sophisticated automatic provers. Because we are working in the undecidable domain, you need to give space for doing manual proofs also. So it has interactive provers. The nice thing about event B, see, proofs usually get very long because you're trying to prove something very complex. I'll just show you how one property looks like. You'll understand what I'm saying. I don't have QoS. Okay, these are, so we'll just read this out. So it says both client and server make sure that no more than one message is in flight. In flight means it's on the way from the server to the client at any one time. Then no QoS1 message will be received after any other later one. The ordering will be preserved. So the way we write it in our theorem proving notation is like this. If you can read a bit of math, this is for all. So it says for all these two variables, if this belongs to n and this belongs to n, if one is less than the other, then there is an order counter which is maintained. If both are within the order counter, then the received order will also be respected. That's what it says. I'm just quickly reading it out in logic, but there is not much to worry. So the thing is, this is like a specification. This is what I want MQTT protocol to satisfy. Similarly, this is another specification. It says something, right? So this is a very interesting specification. So it says exponential back off. So it basically talks about a sender being very perseverant in some sense. So this particular property talks about confirmable message. This might be a slightly non-standard English, but the protocol uses this word. So what it means is that the sender basically perseveres till the receiver gets the thing. That's what it means. And sender has very high levels of perseverance. Suppose it sends now and it waits for 2 seconds, let's say, for an acknowledgement, right? And if for some reason it's not getting acknowledgement, so next time what it will do is it will wait for 2 seconds for an acknowledgement. It's still not got an acknowledgement. Next time it will wait for 2 seconds to get an acknowledgement. So that's what is called exponential back off. So this property is about that. So this, why I specifically put this is it has this thing, 2 into 2 power retransmission counter minus 1. This kind of, the growth of 2 power n is very high. You are able to understand the 2 power n grows very high, higher than n squared or n linear in n, right? So automatic, Gmail client will do that. So automatic theorem provers will run out of steam. They find it very difficult to handle this kinds of growth in function, because So it is difficult to verify these properties. That's why I put this particular example. But a prover like event B can do justice to this kind of difficult properties. So we used event B. We formally modeled 3 protocols: MQTT, MQTT-SN, and CoAP. So I'll not be able to show you the model, but an event B model will look like this. So there is something called a machine in event B. You can think of a machine as a program or a system. So these could be thought of as static variables. So you could say, for example, there are a set of buffers that are available, channels that are available. There are a set of data types that are available, and so on. So each machine could see one or more static entities, and a machine could refine another machine. So this is a very important property, because what you can do is you can initially specify very abstract things and slowly refine it to give details, and do abstract proofs there. And as you refine, you can reuse the proofs that you did in the abstract setting. So that's what is the last step. It says event B supports something called step-by-step refinement to represent systems at different abstraction levels. For example, I might just be interested in one particular thing. So I'll focus on abstraction that concentrates on that. Later, I might add certain details because I'm interested in one more property. Whatever proofs I did at the abstraction hold good. I don't have to redo them again. Event B will ensure that the refinement is consistent, so I can reuse proofs. So it will do that. I don't know whether I'm able to communicate it to you what I said, but it's a very important feature. So a machine in event B has events, variables, and all. You can refine another machine by adding events to it, splitting events and all. And then you say an invariant. An invariant is a lot like a programming invariant. Like, for example, if you write a loop, then we typically write assert. Right? So say that something is an invariant property of a loop. So you could say what is an invariant property of a machine. So you could specify that. A machine is a collection of event. Event is a normal event. So you say a guard or a condition is true, then the action in the event happens. And whenever an action happens, some variables get updated. So this is how the model looks like. So here is a generic representation of a communication protocol. Typically, communication protocol will talk about what the channels are: servers, clients, messages. So for us, they will all be sets, mathematical sets. Then it will tell you what the attributes of a message is: sender, receiver, QoS level, what it is, and what are the properties. For us, those will be what we call constants and axioms. Axioms are always true properties. And then these would be the features of a protocol. It could, for example, transmit, receive messages. It could do, in the case there is an attack, it could produce an error event. It could track time. It could tell you conditions under which you can transmit messages. How do the buffers look like, FIFO, non-FIFO? What are the properties of channels? What are the timers? So for us, these are the models: events, guards, variables, invariants. That's how we model them in event B. So these just tell you how we model. For example, a communication channel, we say, is either multicast or unicast. If it's multicast, then it can support resource discovery, service discovery. If it's unicast, then it supports channel establishment and conversation in the channel. So conversation in the channel could be because there's a timer, because there's an intruder, or these are normal message exchanges. So we go on extending features like this. Each one can be thought of as a machine, which is modeled using first order logic and set theory. And this is just, so for example, there's a machine M which says there are 4 events. These use 3 variables. These 2 events share this variable. Right? In this machine, event E3 is extended. In this machine, event E2 is extended. Some variables are reused. So similarly, something like this happens here. So we go on extending these models and write properties like this. And totally using event B theorem proving, we discharged, this is just the statistics. I'm not giving you the details, but so many proofs were discharged, 1, 2, 5, 9. Usually, when you're working with theorem proving and theorem prover, one of the goals of your exercise is to avoid doing proofs by hand, avoid doing manual proofs, because if you do manual proofs, then the scope of error is high. So the goal of a theorem prover is to push as much of the proofs. If you do your modeling really working hard, I mean, do a good job at modeling, several iterations, then theorem prover will do the proofs for you. So we were able to get about 99.7 proof obligations automatically discharged, but a small part of it was done manually by us. Right? Usually if this number is something like 80-20, it's not considered a good exercise. Because to 20%, what have you done? You could have made a mistake. You could have been working with an inconsistent set of axioms. Why such a high number? Usually not well received in the community. Several papers in top-notch conferences will have 100%. It's difficult to get that number. So this work was published last year in SETA. This is joint work with Maithili, my MS student. She recently graduated in the last convocation. She was working at Bosch. She quit her job at Bosch and came and joined here. So she had good background in these IoT protocols, which I don't claim any expertise over. But because Maithili was from a communication background, she was good enough to learn the logic and the theorem proving part, and we were able to do this exercise. So a part of this exercise is that now we are looking forward to modeling IoT safety critical systems itself. This was just an exercise in protocols. But to model a system of a small kind and to verify its properties automatically will be a big exercise. So we are trying to do that. There is a big group in the UK who are also trying to do. We're trying to see if we can collaborate with them and do. So this is a small exercise in theorem proving. I have about 20 minutes more. The last part will be lightweight. I'll tell you about testing. One work that we did on testing. This is not much math. It's just software development, classical software development. So before I describe our work that we did with software testing, I should tell you about, I'll just go back a few slides and recap. Yeah. So testing begins typically here when I write, this is called unit testing. A programmer himself or herself does. Then here you put together software and components and test, or software and hardware and test. Here you test the system. System means in an embedded software, inputs come from the actual sensors, output go to the actual actuators, right? Like for example, in a car cruise control button, a driver could press switch on the cruise control. So that's an input for us, the switching on. And then set speed. The speed data is another input for us, and so on. So our work that we did in testing is to develop algorithms in here for system level testing. So this was done along with a PhD student of mine called Gracie Phillip. She works in this DRDO organization called Semilac. So before I move on and tell you about system testing that we did, it helps to get some clarity on two kinds of requirements. So at the system level, we typically classify requirements as two kinds. One is what we call functional requirements. It typically requirements that describe what the system should do. Like for example, if you take a functional requirement for a lift, it means as simple as if I press second floor, please take me to second floor. You know, don't be buggy and take me to third floor, right? Or don't stop in between. So it just talks about functionality of a software. The other kind of requirements are non-functional requirements. So they talk about what we call ilities. Is my system reliable? Is my system secure? Can my system perform up to speed? Right? Like for example, suppose I want to go by lift and I press second floor. I expect the lift to be reasonably fast, right? Not doubly slower than what I would do while climbing my stairs. So I expect it to take me to second floor at a reasonable time. Or for example, suppose you log in into your Citibank online, you type your username and password. You expect the welcome screen to pop up almost instantaneously. If the welcome screen takes 1 minute to pop up, you lose patience, right? Typically, IRCTC during Tatkal reservation is not tested for non-functional requirements, right? It has zero latency, zero performance, right? Because it's not meant to scale. So that kind of requirements are called non-functional requirements. Strictly speaking, let you book a ticket, but will it be there? Will it give you screens on time? No guarantee. That is non-functional. Yeah. There could be specification models for non-functional requirements also, like security, reliability. There are models, right? It could, like for example, there are lots of queuing theory and Markov decision process models for reliability and security. So functional means it does what it's supposed to do. Things like very simple, if you have to book a ticket, you can book a ticket. If you have to pay, it will authenticate. If you have pressed button to floor number 2, it will take me to floor number 2. Functionality of the system. Non-functional talks about speed, response time, security, all other kinds of things, maintainability, and stuff like that. Typically in software engineering, we say designers write design and code to meet functionality. What caters to non-functionality is the architecture. What is the server I need? What is the communication bandwidth I need? So architecture talks about non-functionality. I'm not going to go into details about what design does and what architecture does and all, because it's not a course in software engineering, but that's how they bifurcate, right? So for embedded software, which is the focus of my work, there is a specific language, industry standard language to specify architectures. It's called AADL. So popular things you would have heard of are client server architecture and component connector architecture and things like that. So AADL was developed at Carnegie Mellon University. Carnegie Mellon University in the US is the world's leader in developing architectures. So this was also developed at CMU. So it is used for modeling architectures for embedded software. So AADL follows what is called component connector paradigm. So there are several paradigms to design software architectures. So components in AADL include software components, which are processes, threads, packages, and all. Then in AADL, you can also specify system, bus, processor, device. And then you can say what connects what. And then you can talk about properties. There is support for AADL in Eclipse, which is a popular tool. I'll show you how an AADL model looks like. So this is a popular AADL benchmark example. So this isolate system is a neonatal ICU. Neonatal ICU is like, for example, for premature newborn babies, they are kept in what is called NICU. So suppose they are born earlier, 3 weeks earlier, 1 month earlier than their expected date, then they have to be kept in an ICU so that they get uterus womb-like conditions so that they can survive, gain weight, and attain normalcy. So isolate is a system that has a neonatal ICU. So this is just a description picture of the system. So there is an infant, let's say, in the neonatal ICU, and the main goal of an ICU is to keep the temperature conditions of so it's like a box. The idea is the box acts as a replacement of the mother's womb. So it keeps ambient temperature for the infant to, survive longer and attain a level of growth. So there is a thermostat in that which plays a critical role. And there is a temperature sensor which gives the current temperature, and based on what the current temperature is, the thermostat will adjust the heat that it supplies through a heat source that in turn controls the air that goes to the infant, right? So if there is a problem, if it gets too hot or too cold when compared to what is ambient temperature for the infant, there is an operator interface and an alarm needs to be sent to a nurse or something like that who could come and attend to the system. This is like a very high-level description of what an ICU looks like. So this is controlled by software. This is an embedded software for us, right? So I will now tell you how architecture for this software will look like. So this is how an architecture will look like. So architecture says that this isolate system has 4 components. The first component is the operator interface, which is the screen, the nurse's computer screen. The second component is the thermostat itself, which is a device, a physical device. The third component is the temperature sensor, which is also a small physical device. The fourth component is a heat source, something that provides heat. So architecture says that there are 4 components. And what do these things that are connected by all kinds of arrows say? It says that between this component and this component, there are so many ways to communicate. Like for example, display temperature is shown display temperature is a special port that displays the temperature of the thermostat to the operator interface. Monitor status is another port that displays the status of the thermostat to the interface. Similarly, so alarm could be within a range. So what is the range for the alarm temperature is measured at the thermostat, sent to the operator interface. The current temperature is given by this temperature sensor, sent to the thermostat. So what AADL, this is an AADL model. So what AADL model tells you is that here are the components, and they are very like embedded software, because this is just a interface, software interface, whereas these are hardware devices. These components are connected through these interfaces. Is this clear? So this is at a high level. At the next abstract level, it will tell you what kind of a port this is. Is this a data port, an event port? What is the underlying bandwidth and latency of the bus or the wire that supports this port? AADL will let you specify all that. This is different from design. How will you have a design? What is the goal of an isolate thing like you? So there must be some intelligence algorithm built in here which takes the temperature from thermostat, and if it's out of range, immediately sends the thing to the operator interface. What is the algorithm that is used to detect an out of range temperature? That is not a part of architecture. You're able to understand what I'm saying? Architecture gives a static view of the system. It tells you what the components are, how they are connected. That's all it gives. It doesn't tell you how the system is actually built to work. It doesn't tell you that. So AADL is a very popular industry standard language. Huh? Yeah. 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 It can specify that. Like for example, it can, when you say temperature sensor, so there is a library of sensors available that measure temperature, standard out of the market sensors in the AADL. So AADL has this plugin through Eclipse. So you can pull and take it. Or if you say there is an underlying bus, you can say what's it. It could be CAN bus, it could be whatever. All ports, bus specifications, standard sensor specifications, they are all available and you can plug and play. That's a part of the design. Huh. Yeah. So this is the architecture. So design and architecture are done together, right? But they're complementary to each other. Design tells you the actual algorithm of providing, adjusting temperature. You would probably use Simulink or whatever to do the design. But where do you get the heat data from? Where do you have to send the temperature data to? What is the nature of the device that provides heat data? How accurate is the number that comes out of that data? Those are the details that an architecture will give you. So AADL has, it's a very huge language. So you go to this library, you can drop down and get, like for example, in the healthcare domain, they have a library of sensors that they have specified, right? So this is from the healthcare domain. So another popular benchmark specification is a cardiac pacemaker developed by Philips. So those full specs are there, they're sensors. So in the avionics domain, there's a library of things available and stuff like that. So it is static. It'll give you that, and using this, you can design. So suppose somebody tells me that my communication here is through something, right? Then you can design based on the design, bandwidth available, what is the status and all that stuff. So yeah, AADL has support through Eclipse, which is makes it very popular. So what we have developed is, we've developed for 3 kinds of algorithms for system level test case generation. So one is called black box test case generation. Like for example, you could say like from the time in this case, so from the time the infant is put inside the NICU and the nurse switches on the operator interface, the whole system is up and running within 3 seconds. Otherwise, it could be of danger to the life of this thing. So this is a property. So given a specification architecture like this of the system, we can automatically generate a test case for this property. So this is a black box property. So it tells you the speed with which the system should come up. It can't be too slow after somebody switches it on to display the temperature. It should be fast enough, right? So we've developed algorithms for that. In order to develop these kinds of algorithms, sometimes you have to do what is called coverage criteria. I again may not be able to explain what it is. So basically it says that how will the system respond fast enough? System will respond fast enough because from the time this operator interface, like for example, this is the switching on, monitor status is switched on, then what is the cycle in which the system goes through? This gets sent to the thermostat switches on its regulator, then reads the temperature from the temperature sensor, displays it back in the monitor. So it has to go through this cycle. So you trace the path in which data goes through. So that is what is called coverage criteria. So to be able to do this, you have to develop this. So we did coverage criteria for architecture. And the other popular work that people do in this kind of architecture is what is called fault injection based testing. Like for example, what if this sensor fails while the NICU is on, right? Suppose it's gone, battery gone, something, right? How big will that be? How big a fault will that be? Can it be controlled by the system itself? Or you have to raise an alarm and ask for an operator to come and reset and switch on the system. So these things are called fail safe and fail operational. If there is a failure, will the system continue to operate? Another classical popular example is typically you see a small aircraft that goes from Bangalore to Chennai or something like that will have 2 engines under the 2 wings of an aircraft. But let's say if you go from Bangalore to London, you typically see 4 engines under the wings of an aircraft. Typically speaking, for any kind of aircraft, 1 engine is enough. But it always carries 2 or 4 or 6 to be fail safe and fail operational. If 1 engine fails, the aircraft continues to fly. So usually in embedded software that are safety critical, fault injection testing is a very important thing. So they will ask, what if this fails? And do that kind of analysis. Fault trees, they are popular tree data structures, graph-like data structures that will do fault injection-based testing. So we've done fault injection-based test case generation for ADL models. 2 of the pieces of work has been published, one at last year's Digital Avionics Conference and this year's IIIT. One more, we are currently writing it up. So yeah, maybe I'll stop here. I have some slides that talk about this part, how to do fault injection-based testing, how did we do it, but I don't think there's time for that. So a fault tree will look like this. I don't know if you can read it, but you can analyze these fault trees. This was joint work done with one master student who came here from Kerala, who came here for internship. She subsequently joined for her PhD here, Varsha. So this was work done by Gracie and Varsha together. That's why I thought I'll talk to you about it. So we also do, that was 3 of my students' work. I have a few other students. So these are the kinds of work that we do. This is just to list. So I don't know, I may not be able to go through it. So we're trying to formally verify GPU instruction set. We are trying to detect data races in real-time operating systems. We're continuing to work with ABB robots. We want to do motion planning algorithms and test case generation. We also have a sponsored project on Simulink. So these are the faculty. Sujit and I jointly run this lab. Those are the list of my research scholars. A few MTech students, but many Samsung MTech students have worked with us because they like this. And this is just a slide on current grants that we have. We have 1 grant from Royal Academy. We have 2 research scholars from ABB, sponsored by ABB, and 1 grant from DST. So that's it. Yeah. It's an undecidable problem, yes.
Is it because the actual system where your embedded system which you put in place, the runtime characteristics of that system are not completely bounded?
No, in fact, if the embedded characteristics of the system make it bounded in some sense, then you can decide. But it is, what I'm talking about is in general. If I have a programming language, C, Java, whatever, C++, C#, I can't decide. This was Turing's first famous result. Alan Turing's result on halting problem, after which the Turing Award is named after. So he showed that you can't decide whether a program will halt or not. There's no algorithm for that. Yeah. Yeah. Yeah, so it has the digital input, which can be an interrupt, just like a press of a button. I understand. Yeah, I understand what you're saying. So whatever the program says, however it resumes from, we don't care. But for us, where it will matter is here. So the rapid has specifically this. It has this DI. They call it DI, digital input, digital output, which is like a press of a button. Somebody comes and presses alarm, the whole system comes to a grinding halt. So what happens after that? Will the program take care of that, right? So we configure it in the rules. We read the program, read it with our eyes, figure out what it will do in the presence of such a thing, and add a rule to it. So, no, I understand. So you sort of nailed it. This is manually done. If you don't do that, you can't program analyze rapid programs. Yeah, you can't decide things like, will the robot go out of its boundary? You can't answer such questions if you don't have a rule book. Yeah.
So most of the work here is focused on the behavior of one group, the code, the control flow of one group.
No, it's the code sits on the controller. It is on one family of controllers. A controller can control anywhere up to 255 robots.
So do you also model the interference between robots, because they're sharing a state space?
Exactly. Good number of the variables could be shared variables.
So is there any logic for modeling the interference, or is it?
So for us, it comes here. We do the interprocedural CFG. So the interprocedural, one procedure could run in one robot, the other procedure could run in another robot. We don't worry about it. For us, it's as if it's running in the controller. The controller.
Are there any, for example, theorem proving that this set of robots will eventually complete the task without interference?
No, in fact, that's a tough problem. We want to do that. That's this bullet. So we want to use SMT solvers to be able to do motion planning, automatic motion planning that will guarantee safety, collision avoidance, which is the fundamental safety property, and liveness. So together, these two robots being controlled by a controller will paint 15 car doors in 4 hours.